and this fractal dimension is computed starting from the moments of the intensity of wave function psi squared, and then you do certain manipulation and get the fractal dimension, which also can be expressed in the quantities which are known in statistics, in mathematical statistics, like Rene entropy and the Shannon entropy. And if you want to compute Q which is not equal to 1, then you compute you use the Rene entropy, but then when Q is equal to 1, you have to deal with uncertainty, because this logarithm goes to 0, and 1 minus Q also goes to 0, so you should treat this uncertainty, and the way to treat it is simply to start from Rene entropy and then expand this moment in Q minus 1, keeping only the first term, and then you cancel this contribution, and the result is that when Q is equal to 1, you have to deal with the Shannon entropy and for Neumann entropy, and then the formula for dq is the same for any Q, but the definition of the entropy is different. So basically, as I told last time, there are two different pictures which are equivalent, and I show how to come from one to the other, but one of them is to extract the so-called f of alpha function, and for that what you need, in my opinion, you don't need to deal with moments, you need to have the histogram of psi squared, and then you essentially get the distribution of psi squared. Then you can have distribution of the logarithm of psi squared, and then from this distribution of the logarithm of psi squared you obtain f of alpha, and then from this f of alpha you can obtain everything. So to me this picture is more convenient than the one which is based on the moments, and the one which is based on the moments is simply if you want to compute some particular moment, let's say Q equal 2, Q equal 1/2, then of course you don't have to do all this stuff and you just compute the moments. But if you want to know the global behavior, then you deal with this picture. And now I teach you how to read this f of alpha. If you obtain this f of alpha, so how to read it. And so the first thing is to give a physical meaning of certain special fractal dimensions. So essentially there are three special fractal dimensions. So one of them is d1, the other is d0, and the third is d infinity. So these are simple limiting cases which tells you something about the statistics of wave functions. So first of all, this this D1, so what is it? It is what you have to do. If you have f of alpha, then what I want to show is that this tau of alpha, which is the point where the tangential with a slope, certain slope q, where it hits y-axis, this is tau q divided by 1 minus q, it is fractal dimension. But what I want to show is that for this special case, alpha 1 is equal to d1. So alpha 1 is the alpha where this tangential hits the f of alpha. So you take some q, then you make a tangential, and for q equal 1, the tangential touches the f of alpha at a point alpha 1. And so in order to find d1, you simply can do this thing, and this is a useful relationship. So how to show it? It's very simple. It's simple geometry. So you first have the tangential with q equal 1, and because as I shown you before, because of the normalization of wave function, this tangential should pass exactly through the origin, so the tau 1 is equal to 0, and this is since q minus 1 at q equal 1 is also 0, then fractal dimension d1 is final. So first you do first this tangential, and then you do the tangential with some shift in the q, and as a result you have a shift of the alpha, and you have a shift of f of alpha, and by definition this tangential hits the y-axis at a point minus tau of q. So this is just the definition of what tau is. And then we know that there is such a relationship between tau and f of alpha, and then I can differentiate or take a difference here, and what I will get this shift in the tau will be like this, and then since I'm close to the slope 1, then this difference is the same as this difference, because I'm close to the slope 1. And therefore, with this accuracy to the first order in the difference, these two terms cancel out, and what you obtain is that delta tau q is alpha 1 by delta q, and then since tau of q equal 1 is 0, then this delta tau q is just tau of the shifted q, and delta q is q minus 1, so you divide one by the other, this by this, and you get alpha 1 on one hand. On the other hand, by definition, this is D1. So I just have proven that for QE equal 1, alpha 1 is equal to D1. But this is not true if you go to other Qs. So it is only for Q equal 1 that this relationship holds. But then, so this is, then other special point of D1 is that D1 determines the so-called support set of the wave function. So what is support set? Support set is the following. So we know that if we sum psi squared over all sides, over all R, by normalization we should get 1. Now, if we sum not over all sides, but over some part of the sides, then of course we get something which is smaller than 1. Now, let us ask a question. What is the minimum number of this of the sides such that the difference from 1 is of the order of epsilon, where epsilon is a given small number. So more precisely, I need the minimal number of the sides that gives normalization with the accuracy of epsilon. So this means the following, that if I take this set of sides, which is called support set, then this difference will be equal or a bit greater than epsilon. But if I take one more side, it will be already smaller than epsilon. So this means that this is the minimum, the minimal set of sides which gives you normalization. And the question is how this minimal set of sides scales with the size of the system. And the answer is that it scales like n to d1, not to d something else, but like n to d1. And of course, in front there is epsilon, because I want to make this difference arbitrarily small. Of course, this smallness is here, but if I fix this epsilon and increase n, then the support set will increase, but increase like n to d1. This is an important information, because this is the main this is the main information about the wave function, because the wave function lives on a fractal, for instance. Then what means it lives on the fractal? Because there are different fractals. Okay.
I don't know. So I don't understand why epsilon should be there in the support set as a linear factor. Because if you want to go, to very small epsilon, it means you almost you almost sum up to 1, right? So you need more and more contributions. So if epsilon is smaller, your number of considered levels also gets smaller, but it doesn't make sense, or not?
Okay, if epsilon goes to 0, okay. So you are saying the following, that if epsilon goes to 0, then what you expect is that this should go to n, right?
Yeah.
This is what you expect. Okay. So this is this is a legitimate question. This is a legitimate question. So let me answer. It's a good question. Of course, here I mean the following. I mean that n goes to infinity first. So there could be different limits. So the limit when epsilon goes to 0 first, and when n goes to infinity first. But let me look at this calculation, and then okay. So let I explain, and then I tell you, I answer your question. So first of all, suppose I have f of alpha, and I know it. So there are certain properties of this f of alpha, and as I told during last lectures, the combination f of alpha minus alpha, it must be 0 at alpha 1. And this is also the consequence of normalization of wave function. At all other points, this f of alpha minus alpha is smaller than 0. So it is everywhere negative at alpha equal to 1, it is 0. Then there is f of alpha, and what we know that at alpha naught it is equal to 1. So let me first of all express this S of epsilon in terms of the integral of the distribution function. So we know that n to f of alpha minus 1 is a distribution function. Now, if I take the distribution function and integrate over all possible arguments of all possible alpha, which is proportional to logarithm of psi squared, then I should get 1. Then I should get 1. But if I integrate not over all, but over, let's say, from 0 to this point, then what I will get, I told you before that small alpha corresponds to large psi squared, and large alpha corresponds to small psi squared. So if I integrate from, let's say, from here to here, what I will get, I will get the probability to find psi squared bigger than that corresponds to this alpha. So psi squared is, I remind you that psi squared is logarithm of psi squared by logarithm of n is alpha. So then, if I integrate the distribution function over large psi squared until some point, then I will get the probability to have this big psi squared, and the distribution function is f of alpha minus 1, so it is divided by n, since there is log n here, and probability multiplied by the total number of sides is the expectation value. So this is the expectation value of having of the number of sides where psi squared is bigger than some value. Now, of course, here there is some normalization constant in the probability, and I have written it in this way. Simply, when you take alpha epsilon to infinity, then you have probability 1, and this simply reflects this point. But as I told last time, okay, so this is simply the normalization constant. Now, what I can do, I can here is a mistake. There should be f of alpha minus 1, because the normalization constant is the following. I have to integrate if I told you that the distribution of logarithm psi squared is some constant n f of alpha minus 1. This is the distribution of f of alpha. And this, therefore, this normalization constant is 1 over integral of p. So here there should be f of alpha minus 1. I told you that how to roughly compute this integral in the when this logarithm is large. You simply find the stationary point, which is called alpha naught, and at this point f of alpha is equal to 1, and this integral, the main part of this integral, is equal to 1. So you can, then there is some pre-exponent here, and therefore I have written it in this way, but the first approximation, when you add here minus 1, will be that this integral is simply 1. Then you can do the following. Instead of this normalization constant, you can use this one, because in order to have both the total probability equal to 1 and psi squared average equal, and the normalization condition, you have this integral equal to 1 in the leading approximation at large n, and therefore this f of alpha minus alpha at some point alpha 1 is equal to 1, and this is the stationary point for this integral. So when you substitute this stationary point to here, you should get 0, and the entire integral will be n to 0 power. So okay, this I discussed last time. Important thing is the integral in the numerator. Now what I have to do, I have to evaluate this integral, and how I evaluate all such integrals, I do it in the saddle point approximation. So what means the evaluating the integral in the saddle point approximation? This means the following, that if I want to evaluate such an integral, then it depends where this alpha epsilon is. If this alpha epsilon is here, then I can find the stationary point within the region of integration, and this stationary point is alpha naught. And then the integral will be f alpha n to the power L of alpha naught, and this is 1. So then the integral will be dominated by this stationary point. But if alpha epsilon is here before the stationary point, and I am integrating from 0 to alpha epsilon, so then the integral is dominated by the end of the interval. So it is either stationary point or the end of the integral. So that the end where this integrand is maximum, and the integrand grows since it is exponential of f of alpha. This integral grows, and therefore this end makes the main contribution. So what I have then, I have that S of epsilon is n of f of alpha epsilon, because alpha epsilon is the end of the integration region. So it is like this. Now there is there is the second condition, and this second condition determines epsilon. So what this condition means? Again, let us look only at the numerator, because this is almost 1. Now, you see what is written here. What is written here is, as I told you, f of alpha minus alpha gives you the average of psi squared. Now times n. So it gives you essentially the exponential of f of alpha minus alpha times logarithm of n. It gives you integrated, of course. It gives you the n times average of psi squared. Psi squared is encoded here, because here stands q equal 1. If there is some q, different q, then there will be q here. So, what is written here is the following. I integrate from alpha epsilon to infinity. So this means that I integrate over small psi squared. So this means that so what I'm actually doing, I'm doing the following. I ordered psi squared like this, so from big to small. And of course I am taking in this set, I am taking only big psi squared and throw out small. So if I take all of them, epsilon is equal to 0. But if I take only part of them, epsilon is not 0, and it is determined by this part. This part determines epsilon, and therefore, as I told you, large. Small psi squared corresponds to large alpha, and therefore I integrate from alpha epsilon to infinity. So I am actually counting the number of sides which does not enter into into the support set. And this number of sides, this number of sides is proportional to epsilon. So if you take alpha epsilon equal to infinity, then you take then you essentially take into account all the sides in this support set, and then your epsilon should be equal to 0, and this is indeed so. Now, now we compute this integral in the same way, like we did for this one. And here again, there are two possibilities. So now I am integrating to the right of alpha epsilon. And if alpha epsilon, let's say, is here before alpha 1, then the main contribution to integral will be given by alpha 1. But if it is after alpha 1, then as in this case, the main contribution is given by the end of the interval of integration, the end where the function is maximal. So here it is minimum, here it is maximum. So I arrive at a statement that this integral is n to f of alpha epsilon minus alpha epsilon. So I just take into account the end of the interval. So, but this is true if alpha epsilon is between this point and that point. Otherwise, it is not true. Now, then what I do, I exclude f of alpha epsilon from these two equations. So instead of and here let us say what is the result. So epsilon times n of alpha epsilon is n to f of alpha. It is exactly this thing, and therefore I arrive at this result. But alpha epsilon is something that is somewhere between alpha 1 and alpha 0. But now we take into account that I have to take the minimal set of sides, not just arbitrary set of sides, but the minimum set of sides. And the minimum set of sides would correspond to minimum of alpha epsilon. And minimum of alpha epsilon is alpha 1, because alpha epsilon should be between these 2 points. So it can go here, but not actually become smaller than alpha 1. And then I have, and then I put instead of alpha epsilon, the minimum value alpha 1, and alpha 1 is equal to d1, and then I have this result. Now let us think about the question, which is a correct question. So if epsilon goes to 0 first, if epsilon goes to 0 first, of course, the support set should be n to the first power, so I think that this is related with this assumption that alpha epsilon is in between of this and this point, because if epsilon goes to 0, what I should have, have alpha epsilon going to infinity. Only in this case I have epsilon 0. But when it goes to infinity, it exceeds this point. So I integrated, when it goes to infinity, this alpha epsilon should become bigger, bigger, and bigger. Now, when it becomes bigger, sooner or later it exceeds this point. And then this result will not be true, because this integral will be then dominated by the certain point. So I cannot, in this expression, I cannot send epsilon to 0 because I assume that alpha epsilon is between of alpha 1 and alpha 0. And so I cannot make alpha epsilon here. And this is necessary in order to have 0 epsilon. Therefore, this result is true when n goes to infinity first, but not epsilon goes to 0 first. When epsilon goes to 0 first, then you have to put alpha epsilon here and then recalculate all these integrals. So you can do it. Actually, what happens is the following: that when alpha epsilon goes to infinity, then this means that epsilon goes to 0. Then this integral becomes dominated by alpha naught, and or this integral. So if it is dominated by alpha naught, s of epsilon becomes 1. It becomes the following. So this integral and this integral will be then the same, because both of them will be dominated by this point when alpha epsilon is here. And then and then what I missed here, -1, as I said, because the distribution function is just a moment. So the distribution function indeed is -1, f of alpha -1, f of alpha -1. But then in the numerator, this -1 is cancelled because I have to multiply probability by the number of sides, by n. So here it is cancelled, and here it is not. So what I have here is f of alpha -1, and then it will be n to minus first power in the denominator, and this means that n to first power in the numerator. So all these things will be n, as it should be. So when epsilon goes to 0, the support set should be proportional to n. Okay, let me write it carefully. This, when you write, you always do. So you see this integral s epsilon is integral from 0 to alpha epsilon, exponential logarithm of n f of alpha minus f of alpha minus 1. This is the distribution. Then there is a normalization constant, 0 to infinity, log n, also f of alpha minus 1. But there should be also n here, because this is the probability, and I need the expectation value. Expectation value is n times probability. So there is n here. Now, this n cancels this minus 1, and therefore I have integral, okay, I don't have to do it actually. The thing is that if your alpha epsilon is here, if your alpha epsilon is large, then sooner or later it will be to the right of this point, of this stationary point for f of alpha. And therefore these two integrals will be the same. Because this is always given by the stationary point alpha naught. And this also will be given by the stationary point alpha naught. So, so there will be n to f of alpha naught minus 1, and here to n to f of alpha naught minus 1. This is the same, and n remains. So then, when epsilon goes to 0, then the result will be not like this. The result will be n. And this is simply the way to evaluate the integral. So when alpha epsilon is in between of these two, then there will be this result. But then if it exceeds alpha naught, then immediately it will be n to the leading approximation. Of course, there will be some corrections like logarithm of n and so on, but this is what happens. Seem clear, no?
Yeah,
So-
but I still find it a bit strange what it means. I mean, if you say you are already at large distance sizes, and then
So I should have been more accurate in order, I should give both results for this case and for that case, and in the when alpha naught is close, alpha epsilon is close to alpha naught, then I have to be accurate with the pre-exponents. But the main idea here is the following, that I am computing the integrals with the accuracy of powers of n, not with the accuracy of logarithm and other numbers which are in the pre-exponent. And when I do that, what I have to do, I have to find the stationary point for the corresponding integrand. So if it is f of alpha minus alpha, then it is stationary point here. If it is f of alpha, then the stationary point is alpha naught. And then I have to carefully look at where alpha epsilon is, where the limit of integration is. If the limit of integration is where such that the stationary point belongs to this interval, then I will have one result. If the stationary point, if the integration is such that the stationary point is out of the, beyond the integral, the limit of integration, then there will be, the result will be given by the end point. And this is the only difference in this calculation. So it is actually important thing how to evaluate integrals like that. So if there is a big parameter, then it is always the main approximation is that either you put the stationary point if it belongs to the region of integration, or you put the end where the end point where the integrand is maximum. So this is the way to compute such integrals.
Sorry, the question is that, okay, there is this quantity, like the support set, right? Which is, well, kind of a little bit unusual quantity, which depends on the prescribed accuracy, which only works for not too small accuracies, right?
Right.
And
but
how to think
or
about
it
this
works, or
quantity?
it works in the limit where n goes to infinity.
Yes, 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 yes. yes.
I can take arbitrary accuracy, but send
Yes,
that
yes,
to
yes, yes.
infinity.
But-
And ask the question
yeah, yeah.
how it scales.
The question, yes, why this question, how this quantity scales, is so important. What
Because
does it actually tell us?
it is, I'm answering. So, when we are talking about fractal wave functions, so we are always interested how a quantity scales with n when n is big. Because what is fractal dimension? It is the number of sides, how it scales with n. So you take a big n, so it is always the limit n to big, arbitrary big n. And the question in all these fractal problems is how the corresponding number of sides scale with n.
Okay. So if we, for example, would take non-fractal wave functions, then there would be not d1 but just d.
If it is non-fractal wave functions, then, as I said, f of alpha will be steep parabola at finite n, but then tend to a segment, and then you can take a steep parabola and do the same thing. And the important thing is that d1 for non-fractal is equal to 1.
N number of sets. Yes. Okay.
d1
Okay.
is equal to 1.
Yeah, yeah,
And
okay.
therefore you don't have any interesting thing, because your support set is basically always a fraction of all the states.
Yeah, which is proportional to the
Yes,
so
yes,
with the
yes,
accuracy.
yes,
Okay.
yes.
Yeah. Okay. Thank you.
Yes. So you know, in all this fractal business, you are always interested in how things scale with n. Because what is Hausdorff fractal dimension? Hausdorff fractal dimension is defined like this. If you have some fractal structure, you ask a question: what is the number of points in it, or what is the weight if you have a continuous limit? And this weight, the number of points, is by definition scales like n, could be some prefactor here, like n to Hausdorff fractal dimension, let's say h. And this is the main thing in fractal structure. So if you have a non-fractal structure, this h is equal to 1 and no question. So what I wanted, why it is important, because you know the importance, how do you judge whether your wave function is localized or it is not localized? You judge it in the following way. You ask essentially how many sides contribute to the normalization condition, because the main thing is the normalization condition. And if there are few sides independent of the size of the system entering the normalization condition, which determine the normalization condition, then it is localized. If you have extended number of sides, then it is not localized. So if this D1 is equal to 0, this means that only finite number of sides contribute to normalization condition. And this is localization. If
Yes, okay.
if in the normalization condition, in order to have it close to 1, you have to have extended number of sides, so D1 is greater than 0, then it is not localized, it is extended wave function. But it could be extended and non-ergodic, because if ergodic is when D1 is equal to 1. So this D1 is very important, because it tells you, this dimension tells you how many sides, how the number of sides which enough to have normalization condition with any prescribed accuracy, how does it scale with n? Okay, so this is a difficult point, therefore I put it actually, and now easy thing. Now easy thing. So there is fractal dimension d0. So how we find fractal dimension? We should take a tangential with a slope. In this case, slope is 0. You have a tangential, and then we see where it hits the y-axis, and that would be minus tau. So this means that tau 0 at q equals 0 is equal to minus 1. And then there should be q minus 1. So q is 0, so we have fractal dimension at q equals 0 equal to 1. So whatever happens, you must have fractal dimension at 0q equal to 1. So you may have a fractal states, and the fractal dimension is a function of q. It can be, for instance, such that it can be 0 as q is greater than 1, and here somewhere is 1. And if the situation is such, then we say that it is a localized state, right? Because at q equal 1, fractal dimension is 0. So this means that the support set it contains a finite number of sides. But we know that as we go to 0, it should be 1. So that means that somewhere it starts to grow and goes to 1. So it may sharply go to 1, it may slowly goes to 1, but it should go to 1. Even though it is in cylinder, it is a localized state. And we judge if the state is localized in this basis, so it is not localized. We judge what is the fractal dimension d1. Could be the opposite situation. Where the fractal dimension is 1, and then it starts to decrease as a function of q. And if your q equal 1 is here, then we say that it is a fractal state. Even though here we have, if your q is here, if your 1 is here, then it is an ergodic state. Because at q equal 1 you have So this is how we judge whether we have
Vladimir, and this bottom example actually exists in some models?
sorry?
Your bottom scenario actually exists in some models?
This scenario.
Yeah.
This scenario is something that I am thinking right now and writing a paper about that. So the thing is that there is a number of situations, including this recently published or not published, put in the archive experiment of Google team where they essentially find f of alpha, and then and so in this case what they have f of alpha like this, and this slope this is f of alpha. And then something happens with it, but or maybe it goes to 1 and then goes to 0. Right? This they didn't measure, but they know that there is a straight segment of f of alpha, which is k alpha, and this plus, okay, not necessarily going through 0. It's something like that. So k alpha minus something, minus c, or minus tau. Okay, minus c squared. So if and k is greater than 1, and now I can tell you what is the fractal dimension. Just illustrating all what I'm doing here. If I take Q, which is greater than this K, if I take Q greater than this K, this means that I have something like this, and I have to find the line which is tangential to this thing. Okay, let us not count for rare events, and then the tangential will be here. So then you will find that your tau is something, so this is minus tau q, and so tau q is positive, q is bigger than 1, and so you have some fractal dimension. But if you have slope smaller than k, then your tangential will touch this point. And so what happens is the following, that there is a jump in there is a singularity here, because if q is smaller than k, then I touch this point, and suppose that this point goes straight to 1, then that what is then tau q? This is minus tau q as usual. So if this point is 1 and the slope is q, then this thing is q, and this point is 1 minus q. and this is minus tau q. So I obtain tau q is q minus 1. And divided by q minus 1, I will get 1. So fractal dimension dq is 1 for all q smaller than k. So there is things like that. Let's say this k and here is 1. But then, as I said, the tangential will be at this point, and fractal dimensions start to decrease. So there is a jump in the derivative, and so this is a very peculiar situation, because from the point of view of support set, it is an ergodic state. Because at q equal 1, I have d equal 1. But on the other hand, if I take q bigger than this k, then I have fractal dimension smaller than 1. So it is how to think of this state. So from the point of view of support set, it is an ergodic state. But still, if you go to large Q, you have small fractal dimension. And then what they also have in this, so what happens if I have this f of alpha, which is the slope greater than 1. But if I will increase disorder in this experiment, Google experiment, so this slope tends to 1. And so what happens in this case is that this point where decrease start, it becomes closer to 1, but the decrease will be sharper. And then eventually it will be almost a step. So, so you see what will, if it is a step, then what happens? It happens like this. So dq is equal to 1 until q is equal to 1. And then it becomes 0. And at q equals 1, you have a jump. So this is something which is simultaneously an ergodic and a localized state. So it is such a hybrid of ergodic and localized state. So we call it semi-fractal state. And this situation actually happens in a number of systems. So first it appeared in this Google experiment. Then I started to look at the literature, and I found that it is also valid on some graphs. Then it appears to be valid also in the following problem. Suppose you have one-dimensional system with long-range hopping, and you look what happens in the momentum space. This hopping will be not random, so it is just deterministic hopping and some random on-site energy. And this is a very well-known problem, but in fact it wasn't known that if you go to momentum space, then you have also this situation. So
how are these model codes? Is it these droplet matrices, or how are
I should come to you.
what you talked about last, the matrices with long-range hopping, but on-site disorder? Under which name this goes, like long-range Anderson model, or?
No, this is a very well-known model. This is a very well-known model like this. So you you take on-site disorder and the hopping T between sites I and J is simply 1 I minus J to some power A. And it is deterministic.
I understand, but this in the literature is called something like long-range Anderson models, right?
Say it again.
In the literature, this is goes under the name of long-range Anderson models, or
I don't know. So it is called, different people call it differently. So it first have been studied by in some 89 or so. Then it was then we looked at it with Ivan Haimovich, and then in between there was a work which is series of work which is quite known by Malyshev. And so Malyshev have shown.
can you write it down? Can you write it down?
Yeah. So what they looked at is the following. So this problem has the spectrum which is something like that. So it is quadratic on one edge, and it is some fractional power on the other edge. And if you go and see what happens close to this edge, but not in the real space where it is formulated, but in the momentum space, then you find things like that. And this is something which right now I'm writing a paper about, so maybe soon it will appear. But what I'm saying is that this peculiar situation where you may have, this situation of the Google experiment, it is not so peculiar because, okay, so at Q equal 1, I still have fractal dimension 1. And then it more or less sharply decreases. Okay, it is also something which is not well studied, because what people usually think, if D1 is 1, then most probably all others Q which are greater than 1 will be also 1. So if you take the random matrix theory and f of alpha, which is just like this, then what you have that you have fractal dimension equal to 1 everywhere. So you have just, and this was something in the mind of the people. So if you have 1 somewhere, you have 1 everywhere. But this is not the case. So you may have 1 at Q equal 1 and 0 or almost 0 at Q bigger than 1. So this was the paradigm of the ergodic state. And in fact, such things are not very rare situations. So in different systems, it happens like this. Okay, so it is an advantage of few people here. Okay, so then I want to tell you about fractal dimension G equal to infinity. this is the second case where alpha is equal to d. So suppose that your f of alpha has some sharp edge. So let's say it goes like this, and then there is nothing here. Then it is clear that since f of alpha gives you the probability, then the probability of psi squared, which are smaller than n to minus alpha infinity, this probability will be 0. So then this means that there is a minimal, there is oh sorry, no, I'm wrong. So the probability of having alpha smaller than alpha infinity is 0, but psi will be, yeah, okay, psi is always smaller than this. So it's not, and psi square probability of psi square greater than minus alpha infinity is 0. So there is the maximum psi squared that corresponds to this. So, and now what about fractal dimension? So let's take very large Q. And if you take very large Q, then the touching point will be here. Now, what will be then minus tau Q? Then minus tau Q will be alpha infinity, this point, multiplied by Q, because if the slope is Q and this is alpha infinity, then this thing is minus alpha infinity times Q, and divided by Q minus 1. Then I take Q to infinity, I have alpha infinity. So D infinity is equal to alpha infinity. And this is an important thing, because if you have such sharp edge, then this means that there is a maximum psi squared, which is n to minus alpha infinity or n to minus d infinity, and greater than that you don't have. So this is alpha infinity, d infinity, and then you have a generic f of alpha, and as I told you, the part of f of alpha that corresponds to positive f of alpha, these are representative events. So you have many such sites with such amplitudes, because the probability of finding psi squared equal to n to minus alpha, this probability is n to f of alpha. So when f of alpha is positive, then the actually probability is f of alpha minus 1, but then probability density, then you multiply it by n and you have n of f of alpha. So all this part, all psi squared that corresponds to alpha from here to here, they are statistically relevant. So there are many sites with such amplitudes. But the negative f of alpha corresponds to number of sites which are smaller than one in one realization. And if you take many realizations, then you find such sites. So the f of alpha does exist, but this part, why I put it like dashed line, because this is part which is only possible to obtain if you do many realizations. In one realization, you do not find such instances. Then for, let's say, numerical people or experimentalists, it is important to know that if they do just a few realizations, so they do not see this part and they do not see that part. And therefore, typically, they have a minimum psi squared and have a maximum psi squared. So the minimum psi squared corresponds to that, and the maximum psi squared corresponds to this. But if you repeat your experiment many times, then of course you will find psi squared greater than this and psi squared smaller than this. And this is in contrast to this situation, because in this situation, if there is a gap here, then whatever is the number of realizations, you will not see amplitudes which are greater than this one. This is how to read. Okay, now is very important thing, but I don't know, should I start it now or do it next time? So this depends if somebody is waiting for us or not. Nobody. So if you agree to have 15 minutes more, I will explain. If
But
not,
probably they will kick you out in 8 minutes.
Yeah, there is some conference and they will have a seminar here.
Ah, okay.
Yeah, so
Okay,
probably
then we
next
do
time.
it next time.
Yeah.
Then we do it next time because it is actually very important, important thing. Actually, here I wanted to explicitly answer a question of Simon, how to come from Q picture to alpha picture. And this probably I tell right now. So you have, in order to find, to come from one to the other, what you have to do, you have to solve equation, the tau q derivative of tau q. Suppose you know tau q, then you know this function, which is a derivative. Then you solve this function and find q of alpha. And then you put this q of alpha into here, and you have f of alpha. So basically, this is the inverse Legendre transform. You have to solve this equation, find q of alpha, then plug it in this formula which I have derived, and you have f of alpha. So this I will be using because the Milne-Fedorov symmetry, it can be formulated both in the Q picture and in the alpha picture. And I will do it explicitly, but let's do it next time. So you see what I wanted to show you today is that if you see f of alpha, you can read it like, you know, like looking at f of alpha, you can say much, many things about the statistics. And looking at the Q picture, it's, in my opinion, more difficult to judge. But you always can translate from one to the other. So, but you see what kind of translation. We have a linear segment, very simple f of alpha, but it is very sophisticated as d of q. Okay.
Thank you.
Okay, it is good that I leave it for tomorrow.